Hi everyone, my name is Aaron, and this summer I've been working with Dr. Sultan Hassan on constraining cosmology astrophysical parameters using luminosity functions. This is a beautiful thing because usually to constrain parameters we use larger sets of data like the CMB. No one has really done smaller sets like galaxies and luminosity functions. Before we discuss what cosmic parameters are, let's discuss about what the general background of this subject is. So the basic idea of cosmology in astrophysics is to study the origins of the universe and what its fate is. So to study this, we need to find about how physical quantities like act. So the main source of data we currently have is the cosmic microwave background that has been done. And the cosmic microwave background was found after the Big Bang. It was almost 380,000 years after the Big Bang. And we have the standard model, the lambda CDM model, the lambda cold dark matter model of the universe. And it's basically there was a Big Bang, and after that, shortly after, which is 380 years after, there was a cosmic microwave background after the afterglow of the universe, and there was some silence. And then after that, there was a reionization period, and then now we have this. And we chose a specific redshift of 6 for two reasons. One of the reasons is the simulation data that we use, the camels, has the highest redshift of 6. And the second reason is it's in the region where the reionization begins. So it's a very interesting data set to look at. So the basic ideas of the standard model are it begins with the Big Bang, and at large, the universe is isotropic and it's homogeneous. And with this idea, we theorize dark matter and dark energy. And there are cosmic parameters. There are three types of cosmic parameters. There are independent parameters, fixed parameters, and calculated parameters. Independent parameters include like the age of the universe. And what we're focusing on working on is the calculated parameters, like the omega matter and sigma 8. So let's go to luminosity functions. Luminosity functions are basically the abundance of objects in a set. In this case, the abundance of galaxies in a cluster, maybe. So what we're looking at here is this is the number of galaxies per the magnitude and per volume. And this is the magnitude. A magnitude is basically it's characterized. We usually use luminosity functions to define the abundance of galaxies, but since we're using luminosity functions at a high redshift, we choose to use an absolute magnitude. And absolute magnitude and luminosity functions have a negative relation. So the higher the magnitude, it's the lower luminosity function. And we can see that we chose a redshift of 6, which is this. And at higher, as the magnitude grows higher, which means the luminosity is lower, and that means the fainter galaxies. So the luminosity is lower, and the abundance is lower. And this is the start. So we use a power law that was defined in 1976 by a person named Schechter, and it models luminosity functions. And we use a simulations called the CAMELS dataset, and it's built upon simulations itself, the TNG and the SIMBA, and it's a set of hydrodynamic and in-body simulations, and it basically is used to predict quantities that we can define the universe with. And CAMELS is cosmology and astrophysics using machine learning simulations. And we use machine learning to extract information from the simulations and make predictions before we observe data. And there's different types of simulations, as we've seen, the TNG and the SIMBA. So we use CAMELS to find mapping between different simulations. And the CAMEL simulations has different sets of simulations. And the first thing that we did was, since we're using luminosity functions, we wanted to see which parameters affected the luminosity functions. And we can see that only the first 3 parameters affect the luminosity, the equals change, and the other one, this is the omega matter, that is the sigma 8, and that is the stellar feedback. And we can see as the omega matter and the sigma 8 increase, the luminosity function increases. But as the stellar feedback increases, the luminosity function decreases. And that's because when stellar feedback is basically something being ejected from galaxies. So as the amount of matter decreases from the galaxy, luminosity is expected to decrease. So instead of using all the 6 parameters, we started with the 3, and we used machine learning model. So we can't really run camels on an everyday basis because it takes a lot of time because it contains hundreds of billions of data points in the simulation. It's very expensive to run and takes a lot of time. So we created a machine learning model. It has an emulator. We create a training set using the 3 parameters since they're the ones that have been causing the change. And the camels, what camels does is there are input parameters, and then there's camel simulation, and it outputs luminosity function. And then we created a model, training it with the input and the luminosity function. And we created an emulator, and we tested it. As we can see in the next slide, we had a very good chi-square distribution and low RMSE. And a good chi-square distribution, or R-squared, the closer this value is to 1, it means the more accurate we are. The lower the RMSE, the better. So let me go back to the previous slide. And what the emulator does is it takes the job of the camels and then does what camels is supposed to do, since it takes much less time and it's not expensive to run. So we run normally we would run the camels set on the MCMC. Instead of that, we're running the emulator on the MCMC. So what MCMC does is we input luminosity functions into it, and it gets us a set of parameters as an output. And then the parameters that are output are again fed into the emulator, which then outputs predictions. And if the predictions are similar to our observed luminosity functions, they're kept. If they're not, they're discarded. So these are run in thousands of times, and then until we find a convergence. So what we discovered is that with the 3 parameters, we can find the convergence of the sigma 8 in the omega matter, as we can see here, but we're not able to recover the stellar feedback. So this is a problem, right? This test is a fail. This is basically a random luminosity function we took from our testing set, our training set, and we can see that we're able to recover the parameters for the sigma 8 and omega matter, but not for the stellar feedback. So what we ended up doing, what if we removed the stellar feedback parameter and we just trained the emulator with the 2 parameters, the omega matter and sigma 8. And again, we did that, and we were able to recover a somewhat good value of distribution of R-squared and low RMSE, which is good. And we can see that we're able to recover the luminosity function within 1 sigma level, which is extremely good. So this is the true value of our function, and this is the parameter. We can see that the parameter pipeline has been working really well. So what we did after that is we derived new independent constraints based on our luminosity function, which hasn't been done before. And after that, there is the posterior distribution. We can make this tighter. I'll talk about that later, but what we did was basically we derived new independent constraints using observed luminosity functions. There was luminosity functions that have been observed. We got them from a paper, Bounds et al. And the observed luminosity functions have been done with a completely different data set from the Planck collaboration data set. And we were able to recover that within 2 sigma levels, as we can see here, the through value. So we can see that our pipeline method works really well. So, but we can see that our contours are not tight enough. We can make our contours tighter by including luminosity functions from different redshifts. We're just using a redshift of 6. Or we can also incorporate theta constraints by including other like functions such as the total star formation rate. And this is it. So I want to thank Dr. Sultan very much because I learned a lot from him as well. I want to thank everyone at the CCA, NSBP, everyone, and Casey and Abigail. Does anyone have questions? Yes.
So, I mean, this is really cool. It's really neat to see how well you're able to do with the emulators. I do worry with cosmological parameters that this is sensitive to things like how, well, to tie back to an earlier talk on dust, how much dust there is in galaxies, because that can change the luminosity function without changing the cosmological parameters. You know, that there's sort of a degeneracy between escape fraction of the photons and the parameters.
That's a very interesting thing to look at. And in the future, what we're trying to do is to constrain the parameters. We're trying to incorporate more things, like the total star formation rate. So that might make like that a little better. Yes.
You mentioned that you might look at more redshifts.
Yes.
And so will you?
Could you use the seat mic, please?
You mentioned that you were going to start expanding by looking at more redshifts.
Yeah.
And here you were looking at z equals 6.
Yeah.
What's the next step? Will you go to like z equals 5, or will you go to something lower like z equals 1?
So what we plan to do is we're going to see both z is 4 and z is 5 to see the whole distribution in a range. So that will give us a more sense of how the luminosity function changes within redshifts. Yes.
Maybe you said it and I missed it, so I apologize. But how many simulations with camels did you have to run to train on?
Oh, it was 1,000 simulations. So the camels has four sets of data. There's the 1P, then CV, the LH, and the EX. So basically, what we first did was use the 1P to find how the parameters changed the luminosity functions. We don't directly read the luminosity functions from the camels. We have to calculate it using the star formation. The star formation is available in the simulation, and then we read the star formation, calculated the luminosity functions after. And we used the Latin hypercube dataset, which is 1,000 simulations. And that's, we used 1,000 simulations. You can see that our graphs are not, so this is our luminosity functions. The earlier graph was much smoother than the ones we have here. It's because we don't have enough data set. When we were binning them into histograms, there were like 0 points, so we didn't want to include that in machine learning because the machine would learn very differently than we wanted. So we used 1,000 simulations.
That makes sense. Thanks a lot.